So today I wanted to do a little bit of right angle trig review. Now, I know that you know this. However, it's always good to review something when you're going to be using it as the foundation for so many problems going forward. So I thought I would take a few minutes. Please don't be insulted. And maybe, just maybe, you'll pick something up that you missed the first time around. So when it comes to right angle trig, it's as easy as so ka toa. Now, being from New England, I'm careful about the way I pronounce this since a lot of our vowels sound the same up here. So ka toa pretty much gives it all to you right there, where the sine of an angle. Now, sine is just the math name that they gave to the ratio of the opposite side to the hypotenuse of a triangle. That's it. Cosine is simply the math name that they gave to the ratio of the adjacent side to the hypotenuse of a triangle. And tangent is obviously the opposite over the adjacent. Now, opposite, adjacent, hypotenuse, what sides are those of a triangle? Well, it depends. It depends on what angle you're talking about. Now, the hypotenuse is always going to be the side of a triangle that's the longest when we talk about a right triangle, and it's always going to be opposite the 90-degree angle. That's easy. When we talk about opposite and adjacent, it's important to recognize that it's in reference to a particular angle. So what I have drawn here in this very simple triangle is if we use that angle theta. Now, I realize in math class, you normally use A, B, C, or something like that. In physics, we almost always use theta. Sometimes we use phi, sometimes we use gamma, but theta is spelled T-H-E-T-A, and it's a Greek letter. There it is. Now, if I were to write the so ka toa in a different way, I could write it as opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Again, I know you know this already. But here's where the magic comes in. See this triangle right here? This triangle, let's see if I can, there we go. The ratio of these sides stays the same for a given angle. If I were to take that picture that I drew and, well, let me draw it again. But this time, I make it larger. Now, the key here is that the actual ratio of these sides doesn't change. The ratio of the opposite side to the hypotenuse is the same for the second triangle as it is for the first. And that ratio we call the sine. That's it. That's it. And you know what knows the ratio for every angle in the coordinate plane? Do you know what knows it? Your calculator. The beauty of technology is the calculator can do it for you. All you have to understand is the relationships. It knows what the ratio is. So, what's the sine of 37 degrees, you ask? Oh, you punch it into your calculator, and it tells you it's 0.6. What that means is that the opposite side of the triangle, right here, is 0.6 times the length of the hypotenuse. We go back to the unit circle because in the unit circle, what's the radius? 1. Nice. So if we were to draw this triangle, what would the hypotenuse be? Yeah, 1. Now, when it comes to trig, sometimes students get worried that, oh my God, there's so much to learn with it. And that's true to an extent. We can start to look at trigonometric functions in the unit circle, and one of the reasons this is so beautiful is because of its periodic nature. So you saw an animation like this back in the day, and if we were to sort of look at the ratio of the sides of the triangle, they're constantly changing. But here's the thing. We don't need to know that right now. We'll get into it when we get into rotation, but for now, all we really need to know is the triangle. So, what do we end up using it for in physics? That's really the question, isn't it? All right, let me begin. So here's the deal. If I have a velocity that is at an angle, boom. And when I say it's at an angle, it's always going to be to a reference angle, and we almost always make, almost being the key word there, we almost always make the origin with 0 degrees to the right of the coordinate plane. So the reference angle here, I'm going to make to the horizontal, and I'll call that angle theta. Now let's say that I have a velocity of, you know what, I have a velocity v. Yeah, that's easy. Good. Now here's the thing that we've learned in physics so far. Which way does gravity act? Yeah, gravity act, good. Gravity acts down, right? Causing an object to change its velocity. That means acceleration. To have a change in the velocity in the y direction. In the x direction, is there anything that's going to be acting on an object if we ignore air resistance? No, it's not. So there is an acceleration in the y direction, but there is not in the x. So what we end up having to do is to be careful when we're doing calculations. In order to handle that, we have to take our vector and we have to break it up into components. So here it goes. To take that vector v and break it up into components, what I'm going to do is focus on just the x and the y components of that vector. So I can go ahead and label this Vx and this Vy. These are known as the components. They're what add together to give us the resultant, which is actually the actual velocity. Now, how can I, if I'm given v and theta, solve for Vx and Vy? Yep, you got it. I just use right-angled trig. So let's first solve for Vx, okay? So to solve for Vx, and I appreciate your patience here, I can use a simple trig function, right? I can say, well, Vx is adjacent to the angle. So I can say the cosine of theta equals Vx over V. Now, in order to solve for Vx and get it all alone, I'm going to bring the V up or cross multiply. So I'm going to have V cosine of theta equals Vx. Pretty easy, huh? And then all you do is you ask your calculator, what's the cosine of this particular angle? It's going to be a number less than 1, and you multiply that times whatever the velocity is. That's it. Yeah. Let's solve for Vy. So if I solve for Vy, that is opposite the angle. So the trig function I would want to use is sine. So the sine of theta is Vy over V. So cross multiply, I'm going to have V sine of theta equals Vy. And again, all you do is you just ask your calculator, what's the sine? And it knows. Back in the day when my dad was in college, he'd look it up in the back of his physics textbook. How nuts is that? Textbooks. I'm just kidding. So I'm trying to be cool and calm here because I think you guys get this. But there's a few of you that got through it in math but didn't really grasp maybe what was going on at the time. That's okay, because now's the time you get it. So can I try a very simple example? Are you good with that? Yeah, it's a rhetorical question. I'm doing it anyways. All right. So let's go with a very simple angle. Let's say that we have a velocity of 10 meters per second at 37 degrees. And the question is, please find the components. By finding the components, I can then solve the problem of like how far it goes and what's going to happen. All right, cool. Hey, slow down, relax. My next step, I always go ahead and I draw in the components. Now, components are always drawn as dashed lines. I label them as Vx and Vy, always dashed lines for components. Now, Vx is adjacent. So to solve for Vx, yeah, go ahead. Get your calculators out. Now, calculators. I'm going to say the cosine of 37 degrees equals Vx over 10. So I go 10 cosine of 37 degrees equals Vx. So Vx is going to be equal to, that's right, just about 8. Now I'm going to round a bit here. Often for 37 degrees, we can use 0.8 for cosine and 0.6 for sine. So that means it's going in the x direction at 8 meters per second. Hey, let's solve it up for Vy. Yep, some of you already know. That's awesome. You're brilliant. What can I say? Your parents did a nice job raising you. No, I'm not even being sarcastic. They did. That's good. Good for you. You should thank them. So 10 sine of 37 equals Vy. Plug it in. Now, plug it in. Like really plug it into your calculators. If you have an Inspire, you have to make sure that you're in degrees. You're going to have to go to Document, Setting, Degrees, not radians. If you are working on an old school TI-84 like me, you are going to go to Mode up top, right there, and you're going to choose degree. So Vy is going to be equal to 6 meters per second. Did you guys all get that? Good. You still awake? Nice. Bask in the glory of this. All right, I'm back. Now, hey, that's pretty easy, right? Now, that's a step that we're going to take in almost every single one of these projectile motion problems, where instead of things always being fired off horizontally, they're going to be fired off at an angle. So to find the components is going to be key. Another thing that we can do with basic trig is if we have two vectors, let's say we have an object that has a velocity in the x direction, and a velocity in the y direction. Okay, now right now, I have these as tail to tail. Tail to tail. If I'm going to label these Vx and Vy, in order to do what we call vector addition, we need to go tip to tail with our vectors. So the tip of one vector to the tail of the other. As I've done, tip to tail. So the vector or the resulting vector of that is going to be from the beginning to the end. It's on such a roll too. There we go. Now, in order to solve for this, I can just use basic trig to find the resultant. This is, I'm going to go ahead and write the word in. The resultant sounds like a made-up word. It's not. It's the result of adding two vectors together. So to find the magnitude of that, magnitude just means the size, right? It's going to be v squared equals vx squared plus vy squared. To find the angle, now this is the reference angle. It's not the actual heading in the coordinate plane. It's the reference angle to the x-axis. So in this case, I have the opposite and the adjacent side. So it makes sense to me to use tangent of theta equals Vy over Vx. And then at the end, I'll have to put it into the coordinate plane. I think the easiest way to do that is to try with an example. So I'm going to take a velocity in the x direction, an object that's moving, let's say it's at 16 meters per second. And in the y direction, it's running at 12 meters per second. My question is, what is the resultant velocity? So my first step is to go tip to tail. So if I do that, now this time, watch this. I'm going to go 12 down and 16 over. It's actually the same exact result as if I went the other way. Now, I go here, and my reference angle, I'm going to draw to there. Pay attention. Now, to find the magnitude of that, it's going to be v squared equals 12 squared plus 16 squared. I'm going to go ahead and plug that into my calculator, even though I already know the answer, because I'm wicked smart. 20 meters per second. Now, to find the angle, it obviously matters which angle of the triangle you choose. I know that. I see it, which is why I labeled it prominently in the problem. So given that the angle I chose to draw here is opposite the 16 and adjacent to the 12, in order to solve that up, I'm going to say that the tangent of theta is 16 over 12. Now, do I know what angle has that ratio? No, I don't. You know who does? Your calculator. So I'm going to go ahead and say the tangent -1, 16 over 12 equals theta. And then I ask my calculator, what angle is that? Yeah, 53 degrees. Okay. Now, this is AP Physics 1. So, there's always going to be a wrinkle at the end. You and I know that 53 degrees feels like, or does, belong in the first quadrant of the coordinate plane. But my vector is clearly not pointing in that direction. So let's think about how to approach that. Maybe I'll write a note. Put the vector in the coordinate plane. Okay, now I think this is my third time through in class. I've mentioned it a few times, kind of like in preparation for this, so that now this seems like simple, easy review. 0, 90, 180, 270. Maybe it feels like that. I don't know. Now the reference angle that I found, I redraw my vector, and I have this angle at 53 degrees. So how do I figure out its heading from 0? Well, the actual angle would be this, and yeah, I could solve this 3 different ways, but I think in this case, I would do 270 plus 53 to give me 323 degrees. Yeah, you got this. All right, right angle trig review. Whew. That was a slow, calm version. Why? Because it's really important. And if you mess that up, you really don't have a chance on these problems coming up. But you do have a chance because you know how to do it. You got this. All it is the ratio of one side to another on a triangle. And we can use it to break up a vector into components, or we can take components and add them together to find a resultant. Good. Nice. You're at the point now where you have all these math tools in your back pocket and you can just take them out and apply them when you need to. That's where you're at. Thanks for paying attention. Hope you're still awake. Hang in there.